Another aspect of hybridization of atomic orbitals to molecular orbitals is it actually changed the physical shape of the probability density or electron clouds of the orbitals. If you look at the atomic orbitals for the s and p orbitals for carbon, we know that s is spherical in shape and there's 3 p orbitals on the x, y, and z. But we already know that methane takes on a tetrahedral geometry with 109.5 degrees of separation between those bonds. If the orbitals stayed as atomic orbitals, there's no way that that would take shape. The only thing that they would be able to do is, of course, there's only 2 orbitals that had electrons, they would achieve a 90-degree angle with the 2 orbitals. But because these orbitals hybridize into Sp3 hybridized orbitals, they take on a different shape, which accounts and which shows us how the Sp3, the tetrahedral geometry is set up. Those Sp3 orbitals, 4 of them, get as far away from each other as they possibly can because of VSEPR theory again, and that takes on a tetrahedral geometry, Sp3, 109.5 degrees bond angle. The same thing happens for ammonia, NH3. Even though it has a lone pair, that lone pair orbital also hybridizes when it bonds with 3 hydrogen atoms, and that gives us the electronic geometry of tetrahedral for ammonia, which again sets up a tetrahedral geometry and almost 109.5 degree angles. Okay, another hybridization scheme that can occur is when carbon or other molecules like or atoms like it want to form a double bond with an atom, and when that occurs, what happens is we produce an Sp2 hybridization. So what happens if, say, we're going to form formaldehyde, which is CH2O. Loose structures like this. Again, as the atomic orbitals show, we can only accommodate 2 electrons to overlap the orbitals. That would only count for maybe hydrogens, no room for the oxygen. What happens is, to accommodate both or all 3 atoms, the 2 of the p orbitals and 1 s orbital will hybridize to sp2 hybridized orbitals, leaving 1 unhybridized p orbital. Okay, so that will give us this scenario where we have an sp2 hybridization and a p orbital. 2 hydrogens can overlap orbitals here. One of the bonds with oxygen will form with the sp2 hybridized orbital, and the second bond of the double bond actually overlaps with the unhybridized p orbital, and that sets up a very distinct characteristic of a double bond, which we'll see. But that also gives us information about the shape of a formaldehyde or CH2O molecule. Okay, if we draw that Lewis structure again, we've got 3 electron groups. That should give us a trigonal planar geometry. And when the sp3 hybridization or sp2 hybridization occurs, we get 3 orbitals, and VSEPR theory predicts that they should be 120 degrees apart, and they do. But of course we have that 4th orbital, that unhybridized p orbital. How does that affect the geometry? Well, that hybridizes in a different, or that overlaps in a different plane, so the overall geometry stays with this trigonal planar geometry. And here we have pictured the overlapping of the unhybridized p orbitals for carbon and oxygen. So if we would have taken a look at the unhybridized p orbitals before they overlapped, it sort of looked like this, and the overlapping comes above and below the sp2 hybridized single bond between oxygen and carbon. Okay, now this will give us an opportunity to talk about some nomenclature for bonds. It turns out that we refer to as single bonds that occur from hybridized orbitals as sigma bonds. And you can see that with the Greek letter sigma for the single bonds between carbon and hydrogen. Okay, there also is a sigma bond between the hybridized orbitals between carbon and oxygen. we refer to the unhybridized p orbital overlap as a pi bond. So all single bonds contain one sigma bond. All double bonds contain one sigma bond and one pi bond. And that constitutes a double bond. What that creates is a scenario where this bond, the carbon-oxygen bond, because it has unhybridized p orbital bonding, or a pi bond, it eliminates any rotation along this bond axis. It turns out that single bonds the atoms associated with a single bond can rotate freely. A double bond, because of the pi bond, cannot. This sort of acts like a bracket that keeps it in place. Okay, and you can see an illustration of that here. If we have 1,2-dichloroethane, which we can see the Lewis structure here, 2 chlorines bonded to 2 carbons. Okay, all of the bonds shown here are single bonds, so these are all sigma bonds. And these bonds can freely rotate, meaning that at any point in time this dichloroethane molecule can be in this configuration or can rotate to be in this configuration where either the chlorines are on opposite sides or on the same side. But at any point in time it can freely rotate to go back and forth between this and then actually any variation in between. If you have a pi bond, a double bond, that restricts this rotation because it's above and below the sigma bond axis. There's no way that this can rotate without breaking that pi bond. And of course, breaking that pi bond would require energy. Okay, so this creates a scenario where either the 2 chlorine atoms can be on opposite sides or the chlorine atoms can be on the same side. And so now we have 2 separate distinct molecules, and we refer to these as either the cis or the trans form of this molecule. If the chlorines are on the opposite side, it's trans. If they're on the same side, it is cis. Often in the news, you'll hear about trans fatty acids, which aren't very good for us, and that is referring to a fatty acid molecule that has a double bond, and those double bonds are in the trans configuration.